zeros of polynomials, how the roots, solutions, zeros, x-intercepts, and factors of a polynomial function are related. Okay, let's take a look at polynomials. A polynomial expression can be a monomial or a sum of monomials. The polynomial expressions that we are discussing today are in terms of one variable. In a polynomial equation, two polynomials are set equal to each other. Okay, terms are factors of a polynomial if, when they are multiplied, they equal that polynomial. So here we have an x squared plus 2x minus 15. And if you factor that, you'll have x minus 3, which is a factor, and x plus 5, which is a factor. Okay, so the x minus 3 and the x plus 5 are factors of the polynomial x squared plus 2x minus 15. So I'm just bringing these terms back because we need to remember what they are. Since factors are a product, and the only way a product can equal 0 is if one or more of the factors are 0. Then the only way the polynomial can equal 0 is if one or more of the factors are 0. So if we rearrange the terms to have a 0 on one side, such as your x squared plus 2x equals 15, if we move that 15, giving us x squared plus 2x minus 15, this is how, polynomials have been presented to you. This is a quadratic equation. But when we set it equal to 0, and we factor it, and each factor, the x plus 5 and the x minus 3 is equal to 0, see how we can set each factor equal to 0 and we solve. Okay, so x is equal to negative 5, x is equal to 3. That's why I'm always talking about remember to take the opposite number out of the factor. Okay, so the only way that x squared minus 2x minus 15 can equal 0 is if your x is equal to negative 5 or x is equal to 3. Okay, solutions, roots of a polynomial. Setting the factors of a polynomial expression equal to 0 gives the solutions to the equation when the polynomial expression equals 0. Another name for solutions of a polynomial is the roots of the polynomial. Zeros of a polynomial function, okay, remember a polynomial function is usually written in function notation or in terms of x and y. Again, you need to remember that that f of x is really a y, or y is really f of x. The zeros of a polynomial function are solutions to the equation you get when you set the polynomial equal to 0. In other words, the y is equal to 0. Okay, zeros of a polynomial function. The zeros of a polynomial function are the solutions to the polynomial function when the polynomial equals 0. So here's a graph of our polynomial function, y equals x squared plus 2x minus 15. We have a parabola, okay? The zeros of the polynomial are the values of x where the polynomial equals 0. In other words, y equals 0. The zero x value, yes. So here they are. Okay, they're right there on the x-axis. The x-axis is where y is equal to 0. Okay, the point where y equals 0 are called your x-intercepts of the graph. The x-intercepts for our graph are the points negative 5, 0 and 3, 0. Okay, when the factors of a polynomial expression are set equal to 0, we get the solutions or roots of the polynomial equation. The solution roots of the polynomial equation are the x-coordinates for the x-intercepts of the polynomial graph. So factors, roots, zeros. For our polynomial function, y equals x squared plus 2x minus 15. Your factors are when they're in the parentheses with the x value, x plus 5, x minus 3. Your roots or solutions are x equals negative 5 and 3. In other words, we set our factors equal to 0. We found out what the x's are. And the zeros, or the x-intercepts, are at negative 5, 0, and 3, 0. So the zeros, the x-intercepts go together, root solutions go together, and your factors are actually the whole x plus 5 and x minus 3. Now we're going to take a look at what happens when we have imaginary roots with our real roots, okay? So if a polynomial has n-complex roots, will its graph have n x-intercepts? In this example, the degree n equals 3. And if we factor the polynomial, the roots are x equals to negative 2, 0, and 2, which you can see on the graph. We can also see from the graph that there are 3 x-intercepts. In other words, they are negative 2, 0, and 2. However, just because a polynomial has n complex root doesn't mean that they're all real. So in this example, however, the degree is still n equals 3. Okay, it's still a cubic function, but there is only one real root. And that's the x-intercept or root at x equals negative 1, because that's where it crosses the x-intercept. The other two roots must have imaginary components, okay? And they're going to be where that bend in your graph is at, the curve, the bend in the curve. Now we're going to take advantage of knowing one of our roots, the x plus 1, the minus 1, the x equals minus 1, which the factor is x plus 1. So remember that we're going to put down the coefficients from our function, and then the number that we're going to divide by is going to be, that's right, it's going to be negative 1. Remember to bring down the 1, and then it's going to be negative 1 times 1, which will give us negative 1. Remember, we have to add the negative 2 and the negative 1, so then we get a negative 3. Again, we're going to multiply the negative 1 by negative 3. Okay. And remember that that's going to turn it to 3. Then it moves up because we are doing synthetic division here. Add 1 plus 3, which gives us, that's a 4. We're again going to multiply the negative 1 by 4. And we're going to move that over. So then we get 4 minus 4 for a 0. Now then, can anybody tell me what is the quadratic function going to look like? Okay, so all our numbers here, the 1, the negative 3, and the 4, are going to become our quadratic function of x squared basically minus 3x plus 4. Okay, so now we have this quadratic function, but if you start looking at it, you're going to realize there's no way to factor it. Not simple. So we're going to have to use the quadratic equation. So we cannot factor, so we're going to use this. You worked with this a lot last year. X equals negative b plus or minus square root b squared minus 4ac over 2a. So remember, ax squared plus bx equals c. So what is our a, b, and c terms? That's right. A is going to be equal to 1, b is going to be equal to negative 3, and c is going to be equal to 4. We're going to plug them into our equation. Okay? Notice that our negative is going to be on the outside a negative minus 3, which is going to turn into a positive 3. The negative 3 squared turns into a 9. 9 minus 16, though, is going to give us what? That's right, it's going to give us a negative 7 underneath the square root. Well, if I have a negative 7 underneath the square root, what does that mean? Okay, we're going to look at the imaginary roots here. And the imaginary roots, you're right, are from a negative number underneath the square root. So remember, a negative square root is an I. So we can take out the negative square root. Now notice we have two solutions, okay? All right, we always have a pair of these. So anytime you have a curve that does not cross the x-axis, it is imaginary. That's what this is telling us, okay? So for complex conjugates, theorem, what that really means is that root zeros that are not real are complex with an imaginary component. Complex roots with imaginary components always exist in conjugate pairs. Notice that we had an A plus B and you have an A minus B, okay? And that's why they're conjugates. And we worked with conjugates in our complex numbers with the division. Okay, we're going to find roots, zeros of a polynomial. And this is a little different, but this is how they usually present this type of work on the EOC. Okay, so what they do is they give you the factored form of a polynomial function, and they tell you find all the roots. Okay, remember, we can take the factors and set them equal to 0. So we have x equals 0, 5 minus 2 equals 0, and x squared plus 1 equals 0. Our x equals 0 and 5x minus 2 equals 0, these are the real roots, okay? And because you're going to add 2 to both sides and then divide by 5. But what happens here is with the x squared plus 1, we move the 1 over by subtracting 1. We have x squared equals negative 1. And because it's an x squared, we have to take the square root. And all of a sudden, notice that we wind up with the square root of negative 1, okay? Which means um, that becomes an I. Also notice that we have a plus or minus, and because we have a plus or minus, we get a pair of these. All right, let's try this one more time with a different example, okay? Again, we're going to find all the roots of this function, 2x minus 1, a 2x squared minus 5, and then x squared plus 3. So remember, we can take the factors and set them equal to 0. All right. So this time, tell me, what are my real, what is the 2x minus 1 going to become? And then we have 2x squared minus 5 equals 0. We have x squared plus 3 equals 0. Okay, so with our real roots, 2x is going to be equal to 1, so x is equal to a half. The 2x squared equals 5. We're going to divide that by the 2. And again, when we have a square and we take the square root, we get both a positive and a negative answer. Now, in this case, this is a real root because there's no negative underneath the square root. But when we look at the x squared equals negative 3x, and we take the square root of this, now we have an I. And by the way, since I put the I there, that should not be there. Okay? But notice that you always get a pair of these when you take a square root of a square. You always get a positive number and a negative number. Thank you for your participation. The end.